All right. Welcome, everybody. Today is the 15th of February. This is the Dallas Personal Robotics Group Builders Night Virtual. We are going to do the usual thing tonight and roll around the table, talk about projects and questions and ideas, mostly related to robotics, building robotics, software, coding, mechatronics. I clicked the wrong button earlier. Sorry about that. One little bit of housekeeping, just as a reminder. We have this robotic on Discord, started by Murray from New Zealand. A handful of guys are online. If you're interested in joining that discussion, it's a pretty active group. Then just speak up and we can get you a fresh invitation. We're still kind of pending elections. No one's stepping up to volunteer, so I'm just continuing on as interim acting president, whatever, meeting host, at least for now. This Saturday, we got Jack. And Jack's going to show us his journey, his inspiring journey for Coolbot. Maybe if we're lucky, it'll drive to each one of us and bring us a drink. And then there's a handful of other ideas in queue. Various people have talked about it, but nothing's scheduled beyond the 19th of February, basically. So this Saturday, unless someone else steps up, this Saturday is all we have on the roadmap. So before we go further, anything else I should add to this list while we're talking about it? Nope, barring that. So, okay, so we got on deck, we've got Pat, and then John, and then Chris. So Pat, take it away.
So, I've been struggling trying to get communication backbone going for my Raspberry Pi / Arduino robot, Wooden Monster. Happy to say today I have some limited success, very preliminary, but I have a video to show. So I will present my screen.
Get your gold stars ready.
Everybody's ready. Can you see my video screen that's black?
Yep.
So there it goes down the hallway. So you'll see a couple wobbles. I got to tune some PID loops. I've got it going about 15 centimeters per second. And it's going to go to the white tape, which is 300 centimeters. So as it gets close, it's slowing down, and it really struggles to go straight. But then it stops.
Was it programmed to just go straight or actually actively avoiding the walls?
No, it's not avoiding the walls at all. It's right now is just using odometry to go straight. I need to retune my PID loops for the slow speed. It was working pretty good at the 30 centimeters. Decided to slow it down to about 15, and as it approaches the white line on the floor from slowing down, saying, okay, you're approaching target, so it's time to start. Does a calculation basically and reduces its speed all the way down to 5 centimeters per second, and that's where it's having a couple places it's having trouble. So I think I'll put my PID tracking back on and follow through. But I did manage to get a 32-bit OS on there, but I did install ROS Noetic on top of that. And I'm using ROS pretty much just for my... it's doing not too bad. Right now I'm using about 30% of the Pi's resources, 30 to 35. The biggest portion of it seems to be ROS, and my Python well below 10%. They're into 5 to 7% each of a CPU core. So it's not doing bad. I seem to think it's doing a little bit too much on the ROS side. I'd like to figure out why my ROS core is taking a lot of CPU.
Interesting. So ROS core, you said, is the one?
Yeah, so my ROS core is my two top applications. I haven't Pi 64-bit on it and see if I could get Noetic loaded.
Well, it shouldn't be using that much. Now, what's your total usage? I mean, so average usage across all the cores, right? If you just if you make HTOP report kind of the total average.
What?
Can you
I
change
just-
HTOP to report the total average?
Yeah, you can add a little display widget. You can go to setup, and then you can make it basically add an average. It's in so HTOP. Then you go into setup menu, right? Setup, display options. No, meters. Yeah, meters. And then if you go to look through the choice of meters there would be one that's called CPU average. That's what you look.
Okay, I'll take a look at that and see what I get.
Yeah, because then that gets less confusing, right? You look at one process, it says 30%. Okay, so that's 30% of one core. It's sometimes better, I think, to just look at the total, right? What's the total? What's the average usage there across all the cores? Is I think more useful. But
okay, I'll look at switching that over.
the numbers sound a little high. Yes, the numbers sound high.
The other one I had is after discussing your presentation last week, you were talking about Terminator as a terminal replacement. I did some playing around after that with Terminator. Found out that you can, in fact, save the windows. And the other one that I didn't realize it could do is it can broadcast what you're typing in one window to all the windows. So that really comes in handy for when you're logging in with 6 windows to the Raspberry Pi over SSH. You can log into all of them at once. So that was good. I'm not sure if anyone was aware of that, but it comes in handy for working on that. That's all I've got.
Just one more question. So you're not running any of the visual tools on the Raspberry Pi directly, or are you?
No, I wasn't running. I have them loaded, but I wasn't running them.
Okay. Because that obviously will bog down your Pi, but okay, yeah.
Did I
Were
miss
you using
there
the
something
GUI?
about a gold star?
Yeah, I think that's a gold star, right? Gold star for Pat. Yep. First one of the evening. Strong start. Pat, were you using the GUI to shell in? Sure.
I'm using Terminator. I could show you guys what I'm doing. Basically,
Yeah, I mean, there's a lot of things that'll bog down things overall, but if you're saying your ROS core was using 30% of one core, that's already a high number just for that one process. I think that's already high. In a moment, I need to fire mine up to get the reference point, but it just sounds high.
So it looks like it just opens a handful of terminal windows.
part of the way I set it up. So you can see
that's the
all
trick
of them
that
at
you
once.
just mentioned, right? Of typing once and it broadcasts, so you basically get all your 6 SSH connections, like
all at once.
nice.
So I change directories to all at once. Then I go in and I'll turn off broadcast. And so in this case, you can start up broad. And start up my motor routine. So there's my HTOP, and just so my nav, it'll start my motors going. Oops. I've got motors running. You can sort of see what H-top is doing there. So my Ross master is the high one at 29, 25.
So Ross Master, that's the second one in your list, right?
Yeah. So right, 20%. So it's basically that's where I was. So I'll still have to take a look at my my motor serial. I'm using a Ross rate to control the Ross rate.sleep. So it should sleep for the remainder of the cycle at 20 hertz. But I'll have to see what's going on.
Yeah. So maybe are you doing a lot of debug logging?
Oh yeah, I am right
with the
now.
RAWs? So maybe because I don't actually do much of that the RAWs way, but I know that when you do, I think a lot of data gets piped master or RAWs core process, right? So if you're doing a lot of diagnostic output, it's all going through that, and that's maybe why that particular process is using up a lot of CPU, right?
Yeah, as you can see, my terminal windows were all my data was going through there. So that could be it. So I thought all of those were below 10% normally, like below 5. So
Well, cool.
Yeah.
that's sort of it. So
Hey, a video and a demo, Pat. What else do you have hiding up your sleeve there? Okay.
Thanks for the star.
Cool. Good deal. All right. Well, next we have John. John, what you got going on your end?
Yeah, I've added to my Halloween project the face following skull. And as you can see, let's see if I can get this up here without wrecking things. There we go. So I've added a jaw. And as you can see, I'm still moving the eyes here. The problem I'm having right now with the jaw is it bounces. When I move it, I don't know if you can see that. And I think that's because what I'm using here is I've got, well, let's see if you can see this. See if I can lift this up a little bit. My servo over here. There it is. I've got this little piece of piano wire here attached to the servo, and that flexes a little bit. So when I move the jaw, it bounces. Not very realistic. So I'm going to have to replace that 3D printed plastic piece, and hopefully that'll eliminate the bouncing. And that's it. That's all I have for now.
John, you could try a push-pull arrangement on your servo.
I'm sorry, what?
A push-pull linkage on your servo.
You're saying, am I using that?
No, you could. That'll help stabilize it if you could put 2 anchor points.
Okay, well, I'll have to look up push-pull.
Basically a wire linkage off both sides of your horn, your servo horn.
Oh, okay. Yeah, I get you.
So you got to keep it symmetrical, but that may stabilize the jaw a little bit.
All right. Well, I'll try that too. I'll try a rigid plastic piece, and if that doesn't cut it, I'll go with push-pull mechanism.
Well, John, I don't think you have to print something. The RC helicopter and airplane people have solved these problems. Just go to one of those hobby stores, and they sell you all the linkages already made.
Well, the nice thing about designing this and 3D printing the parts is you get exactly the dimensions you need for the project. You have to force fit anything into the project. So that's what I've been doing.
Why spend gas when you can spend plastic?
Hey, John, I came up with something that you might be interested. Share it real quick because other people might be interested in it. It would just take a second.
Well, I'm done anyway.
Yeah.
Cool. Thanks, John.
So is Joff from, God, what was he on? Now I forgot the show. Craig Ferguson. Is he going to have a companion now? That
This came up through my email list. Since I know you're using OpenVino, and this is going to happen next week, I believe. So I'll take this link and put it in the chat. But you might find this interesting.
Yeah, I'm not using TensorFlow. I'm just using OpenVino with the NCS2 stick and OpenCV.
Yeah, but this might you might find it useful. I guess that's what I was saying. Let's see if I can find. I'll just put it in the chat.
What would be the advantage of using TensorFlow other than what I'm using now?
Oh, if you no, this one is probably geared in how you would take the model directly to the OpenVINO format from TensorFlow. So now, if I recall, you have to take whatever model you get. Let's say you're using the MobileNet model or whatever, and you have to convert it into format. This just another way to accomplish the same possible thing.
Well, what I did for this project is somebody already had a model, caffeine
Okay.
model for
Oh, that's even better.
for tracking
Yeah.
faces,
Yeah.
and I'm just using that.
Okay.
But yeah, if you wanted to track different types of objects, yeah, I could get into creating my own models.
Mhm.
Follow my cats.
There's a time well spent. Cool. All right, John, looking good.
can you get it to make commentary by rolling its eyes up in the corner and
Oh, there's a whole host of behaviors I have that once I refine the software. Right now, I have to do things like blink and wink and then move the eyes, and I'm thinking of all sorts of behaviors, like when somebody sees it for the first time and they want to get a good close look at the eyeballs. The eyes will be tracking their face, and as the box around the detecting their face expands, once it gets to a certain point, the lids will start to narrow as they get close, and as soon as they get close enough, snap, the jaws will snap at them.
you could do the chattering teeth in case somebody's going on about Ross for too long, just like
Oh yeah, chattering teeth. There's all sorts of behaviors that that I can add to this. It's gonna be fun once I get the in place. And then I'll add some audio. I'll add a cricket amplifier, get it to scream, get it to say things, get it to roll the eyes.
Which text to speech engine are you going to use? Or are you just going to play audio files?
Well, I was just thinking, I was going to keep it simple for now, just audio files, but text to speech is a possibility too. You can have it react to different situations, have it talk back to people. It's the idea of a somewhat simple project that can spiral out of control and complexity.
Says the guy who's been doing Halloween robots for 2.5, 3 years.
Yeah, well, that's true. It does go there.
It does go there. All right, well, let's see. So we have Chris next, and but no one on deck after Chris. So think about if you want to jump in after Chris.
All right. So how do I show this? So last time, and maybe the two previous times, right, I was showing bits and pieces of my implementation of subsumption on my Romy robot, and I was able to demonstrate that waypoint navigation is working just fine, and I was able to show that obstacle avoidance was working okay. Maybe the movement could be a little smoother, but then I had really the combination of navigation and obstacle avoidance together wasn't really working. It was just turning into the wall, things like that. It wasn't kind of doing both correctly together. And I'm just bringing this up, just brief recap for benefit really of Ross, and you'll see the robot in a second in the video. But what's inside the robot is basically this Raspberry Pi and a couple other circuit boards, each doing some of the functions. And even though in this current configuration I'm not using free RTOS, I have on and off used it on something like an Arduino type caliber sort of boards, just not as low as an Arduino Uno. So you'll find that you do need a little bit of RAM when you use an off-the-shelf RTOS like that. But once you're above an Uno, it starts to actually become practical. And once you have something like a QT Py, which is some Cortex M0 or 3, I don't even remember what that one is, right? Then you're certainly in a caliber of micro that can very easily run something like free RTOS, and that's why my vote goes there, and I think other people would probably also recommend that. So just take a look at that. So that's why I just brought this up. But so now I did integrate navigation and obstacle avoidance, with the help of the suggestions from David Anderson in terms of, okay, well, why not have navigation also look at the at the side looking sensors, and just don't turn when there's something there, right? It's okay to also look at the sensors in that behavior. So that's essentially what I'm doing here now, and you'll see how it's doing in a second, and you'll find it's doing actually quite poorly. So it's pretty pathetic. A lot of room for improvement there, and I'll talk about that in a second. So let me just play this. And so what I'm going to do is first I'm playing it. I'm manually driving. So this is the home location right now. It's X and Y 00. I'm going to manually drive it away. And my waypoint navigation basically is want to go back to the home location, right? So I've driven it away. Now I let go of my controls. And now waypoint navigation and obstacle avoidance is kicking in, right? Arbitrating between the two. And, it's doing that. It'll make it. It works, cutting the corner a little bit here. But so it basically works, but it's obviously not pretty. And just one more time here for kicks, but that's not going to make it any better. And it's just doing a lot of oscillations when it's sort of doing this wall following thing. And I need to figure out why. I mean, I think I have some ideas, but rather than start to sort of hack away at this, I was really spending more of the time in the last week thinking about, just how to go about, diagnosing this kind of situation. Again, I always talk a lot about, and show some of the tools I use that come with RAWs that help you, see what's going on with the robot. But I really wanted to find a good way to sort of, ask the question, okay, why is it doing that? Which behavior is doing what, when, and why? right? And in the past, um, when I had just stuff on from a firefighting robot, I did have a couple different ways to sort of address this kind of thing. Um, One was, of course, simulation, and I don't have a simulation setup right now, which would help, right? If you step through it in simulation, it would help. The other thing I had in the past was I was able to record data and then just play it back through the code and see what the code is doing, with the recorded data. And that sort of is available in RAWs, and I've been trying to sort of make the most of it, and I'll show that in a second. Simulation, again, I've done a whole talk about it. I don't currently have a setup for this robot. I don't have the time. It does take some time to really get a simulation setup working well enough for it to be useful. So I just don't have that right now. But I'm thinking it would actually be a bigger challenge in RAWs to sort of, just by the very nature, everything is a little more decoupled and asynchronous, right? It's not like when you have all your code sort of in one process, if you may, you hit a breakpoint, everything stops, right? That's actually good, right? You can freeze. It's easier to freeze everything that's going on, inspect, right? And then keep going. But now with RAWs, you have all these different Python programs, right? They're going to happily keep running, even if you're in the middle of debugging one program, right? So it's actually some of the things, the way RAWs is doing things is making the kind of debugging that I want to do, or at least have done in the past, a little bit more complicated, unfortunately. So again, I'm trying to figure that out. And one thing that, again, I mentioned, in the past, I would have just recorded all the data as it's coming in and then played it back afterwards. And RAWs does, and I had to sort of, create the infrastructure for that and in a way reinvent the wheel, because RAWs is giving, that's one of the things that RAWs does give you out of the box. And it does come in pretty handy, sort of the ability to record all the data in the system. By all the data, I mean all the topics that are getting broadcast, right, in the RAWs fashion. There is a way to simply just record all of that. And I was doing that. So in that, I'm not sure if it was that run that I showed the video of, but you kick things off and you run a command in RAWs and it'll record everything that it's getting published, right? The LiDAR scans, the IMU that's putting out the current heading, my odometry is putting out, the X, Y, and theta it's calculating. It's also putting out raw encoded ticks for, no good reason really right now, but it's doing that, right? So all that data that's getting published, you can just record. And then you can play it back. And one thing I was doing here is I'm playing it back right now, and I'm just looking at the data, trying to figure out how to make this playback a little bit more useful. Out of the box, you do get the ability to sort of pause, right, and then continue. You get the ability to play it back at reduced speed. But for example, I can't change the speed on the fly. So the playback abilities are a little crude. I'm finding that a little unfortunate, right? Because again, you can't quite sort of control that playback as much as I would have liked. But nonetheless, I mean, this is useful because I've shown similar pictures here while the robot's actually moving, right? You can see what's going on while, but it doesn't give you much time to think and process, right? It's just, everything's just kind of flying by. But if you play back the recorded data like this and pause it, right, then now you actually have time now to look at the graphs and look at the other visualizations and think about what's really going on. And of course, as I'm doing that, I'm just thinking about, okay, what additional information do I kind of need to really figure out what's going on? Because again, you can only record information that's getting published, right? If there's some internal state in one of the logic, right? If it's a state machine, it's in a certain state, or some if statement, you've gone down some certain path in your if statements, right? Unless you're publishing that information of what decision that behavior just made, unfortunately, it in the graph. So I'm realizing that probably what I ought to do, have my behaviors actually publish in this fashion, in just numeric fashion in particular, so that you can graph it, internal state information, right? So just so I can see where that the navigate behavior is, kind of here, or has made this decision, or has made that decision at this moment in time. And then I can correlate that with what the sensors are seeing. I can correlate that with sort of the actions that are being taken, right? So that's what I'm learning now, and means, I have to make some improvement to my code, just so I have this extra visibility of what's going on, just so I can graph, like I said, some of that decision making. But just so you can see this in action, right? So what I'm doing here, yeah, so here's what I'm doing here. This is just what this command looks like, and you recording, all the recording has taken place, and now I'm playing it back. It's called a bag file, and I'm playing it back at half speed, because it's a little easier to follow what's going on. And one of the things you can do in the RAWs, again, time is when you deal with simulation and when you're stopping things, right? You gotta be careful what your code is doing with time. So in this case, it doesn't matter, because I'm not running the recorded data through any code. I'm just looking at it. But what you can also do, and like I said, what I've done in the past, even with a more primitive setup, is you can think of running the recorded data through the code, right? Like the sensor data, play it back, and have the decision-making pieces, listen to it. Now, in that scenario, you have to, again, be careful that your logic, does how it's making use of time, right? Because if you use wall clock time, everything is going to be confused, because as you're playing back this recorded data, it's going to be time-stamped, right, as per when it was recorded. And so that can cause all kinds of confusion. Or when I pause my playback here of data, right, it's what I really want to happen is I want time to freeze, right? So fortunately, in RAWs, if you do it right, and if you use the timers that RAWs gives you, right, then it's just time won't progress when you're kind of in this paused state, right? But again, that means you have to be sure not to sort of use sort of some of the standard timing functions that you might have in your Python code, and I did have that in my Python code. So that's just a side note. I'll demonstrate that maybe some other time, actually running recorded data through the code, and then while I'm doing that, kind of single stepping through the code, right, with the recorded data going on. But again, this is just recorded data playing back, no code running except for the visualization. And so let's take a quick look at those oscillations, right? This is the second run through. So I've I think just given up control of the joystick. So it's about to, become autonomous and turn around, and it's going to try to reach its home point, which is, I think it's this right here. That's XY00, and that's where it wants to get back to, right? And this white line is where those cardboard boxes were, right? So it's going to try to turn around and go back to 00, and it's going to wiggle its way there. So I'm going to hit the space bar here to let the playback continue. And so again, and then you could do things like, okay, let me pause this right here and see what's going on, right? So this is how you would this is how you would use this feature. So I paused it and see what's going on. And now I can inspect either what my virtual range sensors are telling me here and what distance they're picking up, or I could look at the graph, right? And could see, okay, why is it sort of oscillating? Why does it think it's too close to the wall, right? So that's what I'm kind of doing here. And well, you see the distortions in the LiDAR because I'm turning so fast, right? The LiDAR data is getting distorted, but that's not a concern really here right now. But so as I'm looking at this, right, one thing I think I'm realizing, you know, my virtual range sensors that get, you know, created out of the LiDAR data, for forward-looking, my forward-looking ones are really the first three. So the purple one is in the center, right? And then one to each side. So I have overall a pretty wide cone, way too much of a cone in front as to what I consider when I consider an obstacle to be in front. So I think I'm way too sensitive there is what I'm seeing now, right? By just looking at this and looking at, okay, what distances am I picking up in this position? And so, you know, my takeaway is I'm way too sensitive there in terms of the distance thresholds and just how wide my cone is, and I gotta adjust that. So that's one thing for sure. But I just wanted to illustrate that again, kind of advertise the usefulness of FRAWs in a way. But yeah, I see you very nicely see those oscillations, and again, I'm trying to figure out how to better diagnose this, what additional information to really present here to myself, so I can better see, you know, who is doing what, when, and why. And you know, in the bottom left, I'm kind of showing in red the angular velocity that the waypoint navigation wants to command, and in this what is that, the light blue color, that's the angular velocity that the obstacle avoidance wants to command, and then the darker blue is, well, that's the result of arbitration between the two. So you can put all of them in one. Obviously, you can make some sense of that, but I'm finding that a little difficult to follow. Yeah, so that's what I'm trying to figure out. Both, again, how to fix the actual problem, but how to make the process of fixing the problem more efficient, right? By making maximum use of the tools at my disposal. So,
Hey, Chris,
yes.
if I understand right, is it so that you have in your subsumption architecture, you have different entities or behaviors which are each trying to give their input to the arbitrator, but then at any given time, the arbitrator only picks one, correct?
That is correct.
So, but it seems here in these analog kind of graphs that you're showing the values of the different points. But what happens if you just have like an enumerated bar graph or something that shows, well, at this instant in time, it was the avoid behavior. At this instant in time, it was the race forward behavior.
Yeah, actually, good point. And I have some of that coming out in my command line in the consoles. But what I really need to do is, this is exactly the kind of information that I ought to publish, you know, as a RAWs topic, so that I can record it and then later play back and visualize. Right now, I actually have on my, that's why I had we had this conversation about Terminator, right? And nothing is running right now, but right, I had all kinds of stuff coming out on the screen here in all of the windows. But that's of little use, right? When the robot's running, everything's just flying by, right? You can't really make heads or tails of things.
Are you imagining yourself as the architect in the Matrix? Is that what this Terminator thing is for?
Yeah. But so I think I need to, and sometimes looking at it in a terminal is useful, but I think I also need to publish it as sort of topics, because this plotting function, you know, the way it works, you know, just wants to just work with, you know, with numbers. for plotting purposes, and so I just auto spit out some of the decision making results and internal state as a number, and then I can stick it in a plot like that and follow along a little easier. Yeah.
Chris, what is that little black line that it's kind of stays there no matter what?
Oh yeah, this is the measurement tool, and I don't know how to clear it, but basically, right, I can look at the bottom left graph. No, actually, the top left graph is showing me the distance of the front-facing virtual sensor there. But I can just measure, right? I can say, okay, what's this guy actually telling me? Okay.
Oh, and it stays there. Huh?
0.29, and then it kind of stays there, and I know how to clear it. Yeah.
Hmm.
But yeah, so it's a measurement tool. That's actually helpful, right? Because I can say, well, oh, so exactly how far apart are my walls here in this configuration? Let's see. Okay, what's that? 51 centimeters, right?
And those walls are your cardboard boxes, just randomly.
Yeah, so one was the top was a real wall,
Yeah.
and then the bottom cardboard boxes, exactly.
Hmm.
Now, one thing I've always been wanting to do, and I don't know how to do this efficiently without totally bogging down my Wi-Fi, right? Because if you imagine what be maybe even more useful is if you had a top-down view of the robot getting recorded, right, while you're doing this, right, and then you played that back as well, right? That could, I think, be very useful and powerful sometimes, right? So I've always been thinking along the lines of, hey, wouldn't it be cool if I had a camera on the ceiling while looking down and kind of, recording my experiments so that then I can play it back in slow motion and see the actual robot in motion and see what it's doing and whatever quirky movements it's doing, see that a little better.
The scale on the bottom graph, the vertical scale, is that degrees?
That's rads per second.
Rads, okay, yeah.
Yeah, so that's rads per second. So yeah, so 6.28 rads per second. That's a 360 degree per second rate of rotation, right? 2 pi per second in rads, right? That's 360 degrees per second.
Mm-hmm.
Yeah, exactly. That's what it is.
Yeah. Well, I guess by the behavior of the robot and by this graph, you kind of know what's going on. Is as far as like a macro level,
Well, I mean, I know. Well, it's not 100% obvious to me, to be honest, right? I mean, it's oscillating, but is it because there is just some delay in my mechanism that I haven't accounted for, right? And I just it can't turn things around as fast as I'm assuming it can. It's a matter of where I'm setting my thresholds, right? When do I start reacting to my to my ranges, and well, I mean, I there are some delays, and I've measured, and it's not in any of these graphs, but I do know that there is a delay in my when I sort of step on the throttle, so to speak, until the robot starts moving, or even when I change speed or start slowing down and hitting the brakes, there is about a 200 millisecond delay, from giving a specific speed command before you see that, reflected in actual velocity, right?
Chris, does that mean that if your detector detects something and then stops detecting it, that it doesn't stop turning for another 200 milliseconds?
Probably. But again, I don't quite have the full picture of the dynamics right now, right? As to, like I said, I stopped seeing something, right? And then what happens, right? There is certainly dynamics going on here. Some of it having to do with just the physics of the robot. Some of it having to do with, how fast I choose to react, and the ramp speeds up and down, right? I'm not trying to be too aggressive in my low-level motor control. Some of it, ROS is going to contribute some delays too in the way the data gets moved around. So there is a couple layers here going on potentially that add to some of the delays. But yeah, at the end of the day, there is a bit of a delay factor here that maybe more than I've realized so far.
Chris, it looks like your robot's driving right down the alley, right down the center of the alley. Okay. You're not by any chance like trying to wall follow on the right and then wall follow on the left back and forth, are you?
Oh, I'd have to sort of look at the data and see.
Maybe
Maybe it's doing that, right? Again, it's I have to look at it.
Could you move your line of boxes, to give yourself, instead of 60 centimeters or whatever it was, to maybe
really
120, and see if
You're right.
it's running down the center again. Otherwise you may have a special case here of a narrow. You're testing a narrow hallway. You're not really trying to just get around one wall.
Yeah, good point. This could be a special case that I would want to then debug separately and first do a more general case. Yeah.
Yeah, or an easier, or simpler case to start with.
Yeah, I was kind of thinking the same thing. It looks like it's detecting the left wall and saying, "Oh, I got to turn right." Detecting the right wall and saying, "Oh, I got to turn left."
Yeah,
that's why it's going back and forth.
I do know, and it's quite possible because I do know even before I had these two behaviors integrated, I have noticed that when I'm, let's say, turning away from the wall that I'm seeing on the right, I know that I've always been turning too far, and I'm not quite sure why, because again, it's like once you start turning at some point, the sensor is going to pick up really a different reading. But I've always noticed that I feel like it's turning much longer, much further than I was kind of assuming it would, and I need to figure out why that is. And again, maybe it has to do with that relatively wide field of view that I have here, right? So again, there is this,
or David's point
the
about
1 o'clock
the
position, the 1 o'clock and the 11 o'clock position, right? And in addition to the 12 o'clock position, is all part of my front facing, right? I consider that front, and I think I'm way too sensitive in picking stuff up in the front, even when I started turning away from the wall. I think that's part of what's happening. So I keep
Chris,
turning.
I think you're, well, I've got several things jotted down here, but I think your analysis there sounds, I've seen this behavior before in my own robots, and it can arise from a variety of things. But the first is from a latency. That is, as soon as the detector is no longer seeing the object, it should stop turning unless you specifically have introduced a latency. And I'll get back to that in a minute. But that's the one I'd look for first. The second one is that it is, as you suggested, perhaps the case that the field of view is too wide. On my outdoor robot that has the sonar array, the center tooth sonar look out to like 8 feet or something like. They actually see out to 32 feet, but I limit them so that I don't respond if they see any further than 8 feet. But the side looking ones only look out 2 feet. Otherwise you can't go through narrow openings. So you really don't need very much side looking. So that's the second one, that the field of view of the sensors may be too wide. Also, I mean, basically it looks like you got it working, you just need to tweak it. So, the algorithm looks like it's behaving as you expect. So maybe narrowing down, chasing the latency and narrowing down the range of detection. Also, maybe you have too much gain. You don't really need to turn very much, just turn a little bit. If you've got a lot of gain, you've got a lot of turn to recover from. And then what was the third one? Oh, I guess that was the third one.
Yeah,
But
because
I think that it looks like you're almost there, and it's just a matter of tweaking the things. And little tweaks can make it go from working perfectly to not working at all. But I would chase that latency problem first, because that will show up in all kinds of ways. Another thing that can cause those latency problems is the gains in your PID controllers. If they're too swoopy, such that even though you have stopped detecting and stopped sending the signal to turn, it takes a while to quit turning. But it looks to me like all the rest of that is working. Then the last thing I'd say, do you remember videos I showed a few months ago where I just had the robot trying to go in a straight line, and I put a box in front of it? You simplify the kind of problem you're trying to solve so that you don't have so many possibilities. I can actually pull that up here if that would be useful. I won't waste time if it's not. Are you giving a thumbs up there? It's Carl's giving
Let's do it.
Okay, I'll have to share. Does that mean that Chris has to unshare? Let's see. Okay. Can you see anything? No. Present your entire screen. Is that working?
There we go.
You
Yes.
got a rope? You got a robot?
Got a robot.
Okay. So you can see down there, there's a little black piece of tape laying across this yellow marker. And then I've got a cardboard box here, and the robot is right there, set up on its starting point. And what it's going to try to do, Chris, I found it real useful. You were talking about starting and stopping your visualization. I found it real useful just to start and stop the video. You can use that to kind of analyze what it's doing. So that's what I'm going to do here. So here we are driving in a straight line and stop. You see it's just begun to turn to the left. That's because this left-looking sonar has seen the box, and I believe it's set to at about 26 inches or something like that. Also, there's a left-looking IR here, which will see the box when it gets a little closer. So at that point, the navigation has been subsumed. So here the navigation is driving it, and right there, it's subsumed by the avoidance behavior. So the avoidance behavior, and again, you don't have to turn very much. And basically it's going to just turn until the sensor no longer sees the box, which is, okay, there the sonar no longer sees the box. You can see it's shooting past the box, but the IR is staring almost directly at it. And so the IR takes over from the sonar. Basically the sonar, IR subsumes the sonar. And right there, you can see that the IR has cleared the box. Now there's a very short ballistic delay here, so that even though neither sensor can see the box anymore, you see we're not turning anymore, we're going straight. But it continues to go straight for, I don't know, half a second or something before it drops control. At that point, the navigation takes back over and steers it back toward the waypoint. And we can watch the same thing happen coming the other direction. I won't stop it this time. So sonar subsumes their IR, ballistic delay, and then the navigation takes back over. You will see that let me see if I can back that up, that it stops turning as soon as it clears. It doesn't continue to turn. So there's no latency there causing it to continue after it has completed or after the sonar and the IR no longer. I've got one other here where it's a little more like, here we go, where I got several boxes. If you remember this one, you can see then the multiple interactions. So, okay, sonar sees box there, and begins the turn. IR continues to see it, so the IR continues the turn. Now there's a little ballistic delay, so it drives straight, and then it starts to turn back. But at that point, the side-looking IR can see the box, which doesn't really allow it to turn. There, it clears that sensor and can begin to turn, but right there, it stops turning because, again, the side-looking IR can see the box. And so there's that little ballistic delay, which right there ends. Neither can see the box. But at least for the kind of control algorithms that I've played with, it's real important that there not be any latency. And any kind of latency that is there shows up as those oscillations, even if the rest of the algorithm is working correctly. So I would chase that first, and then maybe try to narrow down your field of view.
Yeah, unfortunately, chasing the latency might turn out to be the hardest, right? To chase down, adjusting the field of view and the thresholds I use.
We'll do it first then.
I might do that just because it's the easier one. All right, thank you.
Well, Carl, I have something to show, I guess.
Cool, that's good.
Should I do it now?
Jump right in, and then you're next, and we have no one after you. But David, is that the latest band to put around your head for royalty? Or yeah, okay.
Okay, this is the sonar array off of that Pioneer robot.
It's the roboticist crown.
And Kareem bought a pallet full of these, and I went and hacked up a bunch of broken ones and came away with a good one. He took the other good one. But I've learned a little bit about it. And I mentioned before, Ted, are you here? Where's Ted? Oh, hi, Ted.
Yeah, I'm here.
Okay, I was reading the manual, so the manual is like from 92 or something like that. And they're talking about their odometry. And they said, now remember, the odometry drifts and it won't be very good, so don't trust it past 2 meters or 360 degrees. And I thought, what? These people need to talk to Ted. I was kind of stunned. So we'll have to see how useful this machine is. Maybe this is why we got them so cheap. They're incredibly heavy. It's 25 pounds, and that's without the 3 big lead acid batteries that it expects to use. And there's some other weird things. This sonar array, basically, they've got it set up so that they ping in sequence, and it's 40 milliseconds between the pings. So you've got 8 here and 8 on the back. They actually ping the front and the back together. But that's basically a third of a second. So 3 hertz update rate, which, boy, if you're moving at any speed at all, you're going to hit something and then see it, and all of these, the sonar arrays stick out a little bit in front of the robot, and all of them, the sonar arrays are bent up. So I can assume this probably 40-pound robot moving along at, a couple of meters per second was running into things with a lot of momentum and then saying, I just saw something. So anyway, I went back and I pulled all the pieces apart to see which pieces I might want to actually use. And it turns out that this little control board they made here is pretty neat. Now, I haven't actually powered the thing up yet, and I've got some questions about it. But basically what they've done here, for those of you who are familiar with these SenseComp sensors, they've built a little board that controls all 8 of them, and it has 3 pins that choose which sensor you're talking to. And then they have the standard init, blank inhibit, and echo return, so that you can ping them in any order. I actually don't think you need 8. I think you only need 6. Side looking are not that useful, I've found. We were talking with Murray one time. He was trying to do wall following, and I pointed out that the geometry is such as if you're actually looking and you are following a wall, that means if you turn away from the wall, the distance gets longer. But if you turn toward the wall, it also gets longer. So that's actually not a useful thing to tell you whether or not, it only works if you're already parallel to the wall. Whereas if you use one of these ones that's, say, 45 degrees forward, then when you turn away from the wall, it gets longer. When you turn toward the wall, it gets shorter. So you can actually use that to find out whether or not you're parallel to the wall. So I think if I do use this, I'll only use 6 of them rather than 8. But the little board itself is pretty cool. The way it allows you to do the array with just a single controller. Now here's the question I have. On the, let me see if I can grab one. On the ones I use, it's a big, heavy wire that goes to those sensors. And it's actually a tuned circuit. That is to say, it comes with the connectors on them, and you can't cut those wires and make them shorter or longer, or you screw up the tuned circuit. I can attest to that. So
how do you know, David?
Yes, exactly. And does anybody want to buy one? So, but what I've seen on here is that the length of the wires to each sensor is different length. They're just nicely wired depending on how far away they are from the board. So they can't be part of a tuned circuit. Here's one that just fell out. And they're also this little tiny, ribbon cable wire, which makes me suspicious of the whole thing. I'm wondering, as I say, I can get about 32 feet with the ones I use. And they talk here about 6 or 8 or 10 feet. I wonder if because they're detuned, they don't work as well. In which case it might be better to buy the SenseComp controllers rather than using this nifty one. Anyway, I haven't actually turned it on, so this is all just hand waving. But I did read through the specs. The rest of it, I don't know if I showed y'all. I've got it pulled apart. Let me see if I can hold it up to the camera. Oh man,
You got your money's
heavy.
worth in weight, huh?
Okay. What you can see if you look down in there is that there's actually a pair of motors for each side, and they're ganged together with tooth belts. So my suspicion is they built it with a single motor on each side and found that it wasn't powerful enough to rotate in place. And they had to go add this second set of motors. So while it's beautifully built, and as Kareem said, the best price he found for one of these new was $12,000. But we may have learned a whole lot in the intervening 20 years. And we'll see. I have said before that I have a rule that I don't want to build a robot that's any heavier than I want to carry around. And this one may be over that limit. So I don't know if you can see those sonar arrays mount there and there. There's actually a pair of them. So I got 2 of these, which may or may not turn out to be useful. If you can see those. And then the other question I had, and I've mentioned this before, they have these fixed and basically parallel to the ground. So about 6 inches off the ground in parallel. Since these beams spread about 15 degrees, that means that you don't get out very far before the bottom edge of it hits the ground. And so you're going to get a reflection off the ground. And maybe you can use that, as an edge detector or something like that, cliff detector. But I found it more useful to angle the sonar up, 7.5 degrees. So as that beam spreads, the bottom edge of it stays parallel to the ground. And that way you can see out further. Furthermore, for an outdoor robot where you're, going up and down all over the place. I found it more useful to actually put the array on a servo that's driven by the IMU that keeps it level, so that when you go down over a curb, it tilts it up and you don't just see the ground and try to dodge the ground as you go down. So I'm curious if this could be mounted in such a way as it could be made to pivot and controlled by an IMU. So, okay, so what I'm talking about is making enough changes to this thing that it's very, very, very much unlike what they originally designed it to be. And at this point, I'm really trying to decide, are the wheels and the motors and the basic structure itself worth pursuing? And I guess the reason I say that is because I'm having my doubts. So that's all I got, Carl.
No worries. Sounds good. Ross, jump right in. No,
Hi there, David. I'm sorry to interrupt. Firstly, thanks so much for the invite for tonight. I'm really enjoing it.
Okay, we got 2 Canadians now.
What on earth was that robot used for or designed for originally?
If you look up a Pioneer 3AT, just Google Pioneer 3AT. These were built with the idea that they were going to sell them to universities and research establishments, and I believe they did. A little bit with Kareem, I said, you know, this is sort of like, because he and I both had coveted these when they were new and way outside what we could afford. And now that they're not new and we can afford them anymore, it's sort of like, you know, that mini bike that I coveted when I was 10 years old, but couldn't afford until I was 45. You know, that doesn't necessarily mean it's of any value to me now, but I couldn't turn it up. I couldn't turn it down. The opportunity came up, so here I've got one. If nothing else, I've got 16 of these SenseComp transducers, which are pretty expensive.
But they're originally designed to drive around and pull carts or do some kind of task, or what was?
Oh, they have a whole, there's a flat top on the thing, which they assumed you were going to mount all of the rest of your equipment, your you know, video and your GPS and for whatever research project you had.
I see.
Along about that time,
chassis. Yeah.
yes, the robotics had kind of reached a plateau at that time, and so the sort of fad of the day was, well, since we can't make our individual robots do anything any cooler than what we're doing now, what we need is swarms of robots. Anybody remember that? Robot swarms was the big deal for a while. And I think these were sold. Can't imagine who had the budget, but.
Excellent.
But if you Google Pioneer 3, I believe these are the 3 ATs, they show them in a bunch of configurations. You know, another thing, in the manual, I've read the whole manual now, and it makes lots of references to software long gone that you can get from web servers long gone. And they don't really tell you very much. You know, there's a few places where they define some of the protocols and so forth, but they don't really tell you very much about, they don't give you enough to write your own software. They assume you're going to be talking to their software. So if I do use it, I'll probably pull their processor out and their motor controller out and put in a standard modern motor controller and an ARM processor to talk to the thing. And there'd be plenty of room in there to stick in a Pi, which I can use to drive my cameras and so forth. So that's kind of the reason I bought it.
Throw a pie at it.
Oops. There we go. We got a bunch of these in the group now, Ross. These are the Oak D Lite artificial intelligence camera that can do all kinds of cool things. Has anybody done any more than run the demo?
Not yet.
I've run the demo.
The demo runs good.
Yeah, demo was.
I thought somebody said that they were going to use it to track traffic cones.
Yeah. but I'm not sure that may not need an, otherwise, I think the OD light, the thing that it brings to the party that's different is the depth camera. And I'm not sure you really need that to track traffic cones. You can probably do traffic cones on just a normal Pi camera, or use one of the AI cameras. Well, I shouldn't say open CV cameras that have what's the one that OpenMV, I believe it's called, is
Yeah.
OpenMV or something like that. That might make it a little easier
H7.
because you can use Python on it. But and I think you can you put TensorFlow on that one, or you can put a TensorFlow model, I
It
believe.
runs TensorFlow. It's
Yeah.
built in.
Is it built in? Yeah. Okay.
Yeah.
So that's that's really cool.
But Doug, that was kind of what I was going to do. Basically, what Chris has done with his LiDAR, which is to break it up into a bunch of depth sensors. I was going to use
Yeah.
the depth camera and break it up into a bunch of
I got to
small-
admit, I'm really intrigued by the progress that Chris has made on that. That's really, it's a good way of looking at it instead of handling it. I just want to, something that we sometimes lose track of. I just thought I'd quote this out. Okay, if you have 115,200 bits per second, okay, and you're doing 8 + 1 bits per byte, that's 12,800 bytes per second, or in otherwise to say hello world with an N takes 1 millisecond. To say hello world takes 1 millisecond. So it's something to think about if your code is tossing around a lot of serial port connections, the serial port commands, that it really isn't that, it's pretty time consuming. Just something to think about.
Yeah, usually it's like 1 start bit, 1 stop bit, 8 data
Yeah.
bits. So you're
Yeah.
really talking about 10 bits. So
10 bits per byte.
divide
Yeah.
that rate by 10.
Yeah.
So
I think it comes to 89 microseconds per byte, or 90 microseconds, something like that.
Yeah.
Well, that makes the math easy. So 96K basically is 1 byte per millisecond, right?
Yeah. Something like that.
yeah, pretty close.
So, Ross had indicated that he was looking into LMX, and and he said he talked to you, David. So I'm assuming you sent him the documentation, because I just looked at it, the DPRG GitHub, and it doesn't have the documentation out there. It has a program, but it doesn't have the documentation.
I ain't sent him nothing.
Oh, you haven't? Okay,
You-
well,
There wasn't much for documentation. There was
Okay,
there was a
there-
demo that I
yeah.
had to make work with Platform IO, and then I got it working on the Mega.
okay. I want to say we've ported Dave's original code to all of Arduino, like all of the, I should say, Atmel Arduinos.
AVR.
Yeah, and then it also to the Teensy 3.1, I think. So it'd probably do the whole Teensy line. And then I think you did it to the STM ARMS.
It should run on any of the arms.
Yeah, so I mean,
The only thing that's really specific from one to another, there's about 4 lines of assembly, but more important, you have to be able to generate a 1 millisecond clock.
yeah.
And pretty much everybody gives you that nowadays when in some form.
Yeah. Now, I was looking through my personal, since I did use LMX on some robots, and I looked through and I have some September, I think, of 2015 instructions. I have a presentation that you gave, which is all pings. So that might be useful. And I also had some communication between you and me in email. I copied that. So that's the sources of documentation I've got. And I guess, would you be okay to put that all out on the GitHub, David?
Absolutely.
Okay, so I'll do that, Murray, and Ross, and give me a day or so. I'm slow, and I'll just put it out there into the GitHub.
I must say, I don't think anybody ever caught the pun. This was all based on, oh, help me, Carl, Ciarcia.
Dave Ciarcia, Circuit Seller.
Dave Ciarcia, Circuit Seller. He wrote an article, this would have been like in the 80s, called A Lightweight Multitasking Executive. And that's why I named this LMX, but it was really a pun. It's as if someone was pronouncing Linux, but they had some speech impediment. Linux. And of course, it's changed considerably over the years. It's gotten smaller and faster.
Mm-hmm.
And it's really, the AVR implementation works, but it's a little klutzy. The 32-bit processors, it runs a lot better on. Things that on the AVR take 10 or 12 lines. On the ARM will be one instruction. So it's a lot cleaner.
Ross, have you had it run the demo program with the 3 LEDs?
I did that first, and then I'm starting to port over my just some of my simple motor control sketches over to work it, because the little bot that I made with a Lego chassis and some motors and stuff, my daughter and I were playing around with it, and I could make it drive around and do a little kind of a I don't know, jitterbug kind of dance for her. And I put a piezo speaker on it so it would play 8-bit tunes, but it wouldn't dance and sing at the same time. So I went looking for a solution for that.
Yeah.
And then I said, okay, well, I can code my own solution using like wait for milliseconds or wait for, stuff like that. And then I thought, well, this is silly. Someone else has done this.
Yeah.
And I went looking for it, and I found a couple other solutions that were just kind of other. One was called a ticker, I believe. A ticker timer is very kind of a similar idea, and someone else had cloned, or sorry, not cloned, forked libtask. They call it libtask, or is it LMX? I'm not sure which, but it's libtask. Somebody with the name of Undefined or somebody on GitHub. I don't know who that is.
So is your daughter interested in being an engineer?
She's interested in that and having her nails painted. So it's a toss up between the two. Depends. She likes the drones that I've been playing with, and she thinks it's pretty cool to sit on my lap and check out little blinking lights and tones and stuff. But
yeah. You never have too many blinking lights.
Yeah, no, she's 7, so I made a little light organ thing where you could plug in some music, and it was streaming the the LEDs at different tones, like different frequencies would hit the different colored LEDs. And I thought, that's an electronics project that I learned back in the 90s, and I'm thinking to myself, like, someone must have done this with an Arduino, and then I look and saw like the nanos, how cheap they were, and I get like 5 of them for $30 shipped to my door or something like that. It was crazy. 30 Canadian dollars, which is Mexican money for you folks. But
I'm looking at this group, and the average age is pretty high, but we're really kind of the product of an age where women were discouraged from going into a STEM. Hopefully that has changed.
No, I think she's got lots of opportunity. She's in a good school, and she's just kind of feeling it out. She's into music and dance, but she wants to play around with the robots is kind of something that she was interested in, but she doesn't really have an understanding of the technology that would be required to make it.
Well, yeah, at 7,
she wants it to bring her a bowl of ice cream from the fridge,
Don't we
Yeah, like-
all?
Yeah, yeah, exactly. And she said she wanted one that she said she wanted one that would patrol the house, and if any bad guys come in, would bite them in the bum.
There you go.
So I thought about making a motion tracker, a motion sensing and light following robot at first, and then just
Mount
play
a
it.
cattle prod on it.
You could get John's eyeball job.
Well, I have one of those me-arm kits that's made out of aluminum, and I'm going to mount it on the top of the bot, and then be able to control it with the joystick, and then eventually be able to program the arm. So I'll be able to locate the arm around with the base, and then the arm is going to be able to, I don't know, pinch you, I suppose. I don't know what she's going to make me want to or want to make me do with it yet. So.
Ross, I would add one other thing, just editorially, concerning an RTOS.
Okay.
It really takes some thinking about where it needs to be used and where it doesn't. The most powerful function that it gives for me is the ability to delay a certain amount of time so that other processes on the robot can run. So for example, a lot of us here use a 20 hertz or a 25 hertz control loop, where you read your sensors and you do your calculations and you write your outputs, and then you wait for whatever is left of a 50 or a 40 millisecond time window. And that can be done in an Arduino style world just by, sitting there and spinning on a timer, but nobody else gets to run. So it's really wasteful of CPU cycles. That ticker that you mentioned I've looked at it before. It's a really crude way of doing what's simple to do with an RTOS, which is a way of trying to set up tasks and switch between them while they're delaying. You don't really have to think about that. But there are certain things that an RTOS is not well suited for. And so it really takes some thinking about what tasks should be run as separate tasks and what tasks should be part of the control loop. One of the things Chris was talking about a couple of weeks ago in the implementation that I brought up last summer, basically most of the robot runs in a single big control loop. All of the behaviors run in turn. An arbitrator runs when they're all done and chooses the output and sends it off. Then there's a delay where other things like the user IO, the telemetry, the delays for the sonar and so forth run. But most of it runs as one big loop. And I had in the past broken those out into separate tasks, which is what Chris was doing. But I just had a hell of a time with synchronization. It's one of the reasons that I've been kind of fascinated by what he's done, because he's actually dove in head first into a process that I walked away from, So I'm eager to see the solution and how that's made to work. But it's not trivial. If you run all of those tasks in a single loop, then you know that they're all synchronized. If you run input tasks at the top of the loop and behavior tasks later in the loop, you know that the behavior tasks are using the most recent data, and they're all using the same most recent data. So there's a lot of good reasons to not make those separate tasks. That's what I mean by it really requires some thinking about where the RTOS should be applied and where it shouldn't be applied, where it actually makes it harder to apply it. And I think that's all I had to say. I can always keep talking, but I think I'll stop.
Well, I guess my question then about that is that, whenever you do use the scheduler, task scheduler like LMX, and if you're using it in a way that is just for simple projects, is probably a lot easier than if you're going to have to run something that's going to be well coordinated, I suppose.
Let me see if I can find an example of what I'm talking about. It requires me to look at things. Hang on here. Present entire screen. You guys have a screen with code on your screen?
Scratch code.
Okay, this is the main task for the RCAT robot, the one I was showing earlier. And so we're going to ignore stuff going on here at the beginning. It goes down to initialize, and there's a system init which initializes the RTOS itself. And there's a library init which initializes everything in the library, and then a user init that initializes all my own tasks. And then basically, I'm going to create a bunch of tasks here. And so you can see it says create task, and it gives an ASCII label and the task itself. And it passes in an argument, and then it has a certain amount of stack size. You can see that the task created, there's a sign-on task, there's a print task, which knows how to print to the LCD. There's an idle task, which is basically a logger task. And there's a GUI, which is my interface. There's a reload task, which is just runs quickly and reloads things if they're broken. And then it says create a sensors task. Well, that's really the whole robot right there, the sensor tasks. All the rest of those things, there's some things to run some sensors. There's the bump sensor and the IR sensor and the ping sensors and the IMU, and there's a gyro calibrate and so forth. But most of the robot is running in this task here, create task sensors. And if we go look at it, if I can find it, it wouldn't happen to be named sensors. That would be too easy, wouldn't it? So basically, this is it, this loop here. So we're in an endless loop that that runs some tasks. We run the odometers and the speedometer. And then if we're operating, it runs these behaviors. There's a remote control task where I can steer the thing around with a key fob. The prowl task, which is the default. There's the navigate task, like Chris was demonstrating. The bumper, the IR, the sonar, a stasis task that checks to see if the robot is stuck. There's a boundary task where it can stay inside of a boundary or outside of a boundary. A wall follower, and all that's followed by the arbitrator. And then down at the bottom, you see it says wake after. Well, that's the only call there. None of the rest of these call the RTOS. This is the only place that the RTOS is called in this whole thing. So most of what controls the robot is, in point of fact, run in a big Arduino style loop. In the Arduino RDE, it's a little hard to tell what's going on because they have some stuff running behind the scenes they don't tell you about. You can get rid of that, which I do in the implementation that you set up. But they're doing some other things behind the scenes to try to facilitate all that. But basically, you have this one big loop, and the only place the RTOS is called is at the bottom of that loop to handle the delay. And in that delay, all the rest of those things run. So I don't know if that makes it clearer or less clear.
Yeah, I'm sorry, I kind of lost track of my my question earlier, and it was more about when we were talking about trying to juggle the scheduling or juggle the timing, I think is what you said. And I'm wondering, like, when you break it out into different tasks and whatnot, like, are you using like a lot of finite state kind of
Yeah, let me
flags
pop that
or
back up.
semaphores, I guess, in that way? Is that how you're managing that?
I think the answer is yes. We pop back over here. So each one of these tasks, and I can pull one of them up, we can look at, let me find a simple one, are basically little finite state machines. So this is like running each one of them in series. They're not run separately. So these are all just calls. Let me pull up the IR task, and maybe that might make it more clear. Wouldn't be something here named IR, would there? Yeah, there's one. Okay, so here's that task itself. And basically it checks and says if this task is enabled and if we're arbitrating and certain things are true, that we read the IR. And then based on that, we do a switch, which says if it's a left detect or a right detect or a center detect, we output velocities and rotations. And that's just basically the whole task. So it's not as easy here as I thought it would be to describe, but it is basically just a state machine that's based on what it was last time running through and current state of the detection. So there's no calls to the RTOS here. This is just a subroutine. And in my case, each one of these returns a void and it expects a void. So when they're called, oops. Here in this big loop, wherever they were, at the end of the main, which I didn't get to before, after we've created all these tasks, the last thing it does is call the scheduler. So main never actually exits. The scheduler then begins stepping through these tasks. And, you know, it's a cooperative multitasker, which means that each task has complete control of the microprocessor until it releases to the next task. So interrupts everything. There's no supervisor, if you will. But that, I think I could make all of that run on a machine without an RTOS. It would be harder, but the RTOS makes things easier, but it's not strictly speaking required. And I don't know who else in the group actually uses an RTOS. I mean, the ROS people obviously are using ROS as their RTOS.
Mm-hmm.
And you may have to change your name because it's too confusing when we have a robot operating system everybody calls ROS.
I was just feeling very popular. It was great. You're a very welcoming group. You talked about me all night. It was except for the gripes, you know. Well, thanks so much, guys. I'm you know, really excited to see a little more about this. I have to go do some bedtime duty tonight. So, good night. Thank you all.
Nice. Good night. Jump back anytime you like.
Okay, I'm pretty sure I got Rudd to start showing up and Paul, and now I've added a second Canadian. Oh, Doug, we'll need a new set of stars.
The influencer star. David Anderson, TikTok influencer. Here we go.
Well, Ross sent me an email yesterday just asking me some questions, and I wrote back and I said, but you know, probably an easier way to get these answers is just to show up tomorrow at our online meeting. And
he mentioned that he found must have been one of your presentations or something on YouTube, and that's what he was searching for one of the multitasking kind of a thing, and I think he found one of your presentations. Then he reached out to you, and so YouTube as search engines working for that for DPRG.
YouTube is forever.
Yeah. Cool. All right. Well, we've gone around a fair bit. Who else has some things to share tonight? Oh boy. I don't. That was like I was helping my mom clear out the house and such. One of the things is an antique car, so I may be splitting my time between robot fun and antique car fun. So we'll see how that goes.
Yeah,
Does it run?
I'm on the second law of Ackley, you know, second and third steps. So
I was going to say, if it runs, you know, you can sell cars now for outrageous prices.
Yeah.
Clearly, I've become infamous. My rule of three.
It's a good rule. But Ray, if you're on the second one, does that mean the first one ran and now you're working on number 2 to run?
Well, I had, let's see if I can do this here. I can show you here real quick. Boing. The mill that I was working on, the ratio out of the stepper was way too low, so there weren't enough steps per millimeter, and so I had to buy a 20-to-1 gear head to put it in there between the two. So that's the second step. I'm hoping there's not a third step, so maybe I can only take it to the second step.
So how many steps per millimeter does that give you?
I have to figure it out. It's like, I think it's in the 70s, 74 point something. I forget what exactly.
Wow. Is that what's required?
Okay, and then times, let's see, so 20-to-1, I didn't figure that out. Okay, so 200 steps, 20 times, A, divide. 93, actually it's better than I thought, 93.056 steps per millimeter. Yeah, if you don't have enough, like it goes down, the lowest number is 5, but at 5, you can only move like 2 millimeters. So it doesn't, it's not fine enough resolution. I really need to move like, at least 1/10 of a millimeter and preferably 100th of a millimeter. So.
And you're at about 100th there, right?
Yeah. So, that gets you down to 0.01 millimeter, which is pretty small. So yeah, I found that out. I hooked up the Z-axis stepper motor and had it move just 1 millimeter, and it moved like, that much. And it's like, oh my God, what the heck is that about? And I couldn't get it any smaller than that. So, because like for positioning, you usually position on the top of the workpiece when you start off. And, that has to be a pretty fine adjustment because you don't want to drive the bit into the piece, whatever it is, mill or a drill or something. So, yeah. So, but hopefully by next Friday, I'll have put that in there and I'll, have 20 times better resolution because it's a 20-to-1 gearhead. So
you're not using a incremental, on the stepper motors, you can, do quarters, eighths.
Yeah, micro stepping. Yeah. That actually doesn't help. That just makes the drive patterns more sinusoidal versus like a square wave or a hard step. And you can actually increase the torque out of the motor that way. But it's basically down to whatever steps the stepper motor has. Like that one's a 200 step per revolution or 1.8 degrees. So you need, something finer than that, either a lead screw to, spread those 200 steps over, maybe, I think like the 8 millimeter, 2 millimeter pitch ones. That's 100 steps per millimeter exactly. So that's kind of nice. And that's what's used on a lot of the 3D printers.
So this took you from 200 steps per revolution to 4,000?
Yeah, 20 times 200 is, 4,000 or 40,000. I don't know which.
How much backlash do you have in those gears?
They're not supposed to have that much. It's in, I think in arc seconds. The I don't think it matters that much. Most of it's kind of like in 3D printers, you don't need anti-backlash nuts on the Z-axis because you always have the weight of the Z-axis on it from gravity. So the downforce is what's significant on a mill because you're always cutting, from the top of whatever material you have into it. And so the up force, it doesn't really matter if there's that much backlash there.
Meaning that you're not cutting on the upstroke, you're only cutting on the downstroke.
Really, yeah. You're pushing the whatever it is, the end mill or the drill into the workpiece. So
'Cause I've seen on robots that even with a small amount of backlash, as the robot slows down, you're jumping back and forth.
right. Yeah, and it's chain drive. I've got a tensioner for the chain, but and it also increases the amount of torque on it. It's just a drill press, and the drill press just moving the I'm not certain what it's called. It's the mechanism that lowers the quill, or but one turn is like of that is 4 inches of downward travel. So it's it's geared kind of high in comparison to what you really want it to be. You don't want it geared nearly that high.
But that's what you'd want if you were doing it by hand, right?
That's right. Yeah. You don't want to have to, screw the thing around because you may not be able to. Yeah. So it is a drill press after all. So, but yeah. So that's kind of where I'm at with it. So I was like, really excited, got the Z-axis motor hooked up and I'm testing and it's like, oh boy, I guess I got to adjust that. And it's like spinning the little knob and it gets down to 5 and stops. It won't go below 5. And it's like, oh no, I'm screwed. So that's why I had to get that gearbox. So, because without the gearbox, it was like 4 something. And that's what I was trying to get to. And it's like, nope, can't go that low. And then I realized the resolution was poor even at 5, 2 millimeters basically, which is only as good as I could get it to. But anyway, that's what I've been up to.
That'll keep you busy.
I'm hoping for the optimistic end of the delivery. They said it could come by Friday, or it could come, I don't know, next week sometime.
June.
So I'm hoping for Friday.
Cool. Right. Anybody have plans for next week? Some builds they're going to try and pull off? I'm just going to try and pull off a meeting on Saturday. Call it a good week.
So did you get the car home yet?
Oh, hell no.
Oh,
No.
okay.
It's a 1957 Mercedes 190 SL. And it hasn't run since 1964. It's sat in the garage. So this is going to be quite a project.
So is it a diesel or gas?
Oh, it's gas. It's gas.
Okay.
Just when you go to start it, make sure you have a fire extinguisher nearby.
There's
You might check the rubber hoses on that. They could be, yeah.
might
maybe
there's
replaced.
there's a lot of hours and some bank draining between now and then. Bank robbing, maybe.
Yeah, I don't know if I told you or not. I have a 2 1965 Chevy C10s, one that I've restored and one that I think I'm going to try to sell to the Pickups and Panels Club in Dallas because I've got another vehicle that I wanted to put a engine transmission combination into. And trying to get that thing home from my father-in-law's, I rented a tow bar. And so the there's, the front end parts were missing on this thing. So the wheels, weren't attached, front wheels weren't attached to each other. So they're going in all directions, and get those up on the tow bar. And I had to use my spare tire from the truck that I restored to put on the back of the one that I was towing because the tires are all rotted out. So on the way home, I have this really bad blowout. It's like the tire just destroyed itself. And I had another old tire that was, for some reason, was still holding air. I don't know why. That was the only thing I could put on the back of the truck because it was my spare that blew out. So, I imagine just to get it home, and it's like, so. And that was only from Mesquite to, north of
Yeah.
McKinney. So I can't imagine a cross country trip, that's
It's going to be hired, I'm pretty sure.
wow.
We'll see. It'll be a long project depending on what I do with it.
Yeah. I don't think that's going to be cheap. I think cross
No.
country.
No,
is
not
like
a bit of it's
thousands
going
of
to be cheap.
dollars, maybe.
Yeah. I don't know.
Yeah.
Ask me when I figure it out.
Oh.
Apparently, it costs more if it's not a running vehicle. So, and I
Oh,
don't think it's
4,000.
it costs
Oh, it
more.
costs more.
It
Oh, I
costs
thought you
more to
said four.
transport a dead weight than a running vehicle.
Yeah. Yep.
So,
Somebody's got to push it up into the thing and push it back down again.
Chris, you have a hand raising.
Yeah, so I think Pat is still on. Unless someone else has something, I have just one quick follow up to Pat's
I'm still
sort
here.
of problem.
So,
Okay.
incidentally, I did a test following your advice, and I turned off my logging, and my utilization went way, way, way down.
Okay. Yeah. I figured that was it, but I just wanted to show as a reference point. I took a screenshot earlier. And so the top two items there on my list are both pieces that are pulling data out of one of my microcontrollers at a rate of 100 hertz, right? The Cutie Pie is dealing with the IMU, and so I'm talking to the Cutie Pie, pulling data out at 100 hertz and moving it around. And the second one is my odometry node, which talks to the main microcontroller control board and pulling, encoder ticks out of there and other things, again at 100 hertz, and then publishing it to whoever needs it. And so because those two pieces operate 100 hertz, right? They tend to be on top here, and then tends to fall off fairly quickly. There's a LiDAR thing going on here, but we're already in the single digits of percentage, right, of one core. Again, my total in this case was, where am I? Oh, where's my mouse? I realized my mouse was in the wrong place. Total is at around 10% of everything, and these numbers here are, per core. So again, anything that's doing work at 10 hertz, 20 hertz, it's just going to be in the single digits. But the stuff that's at 100 hertz for me, and then maybe that's overkill, but that's where it shows up. And the moment you start consuming information that's coming out of these nodes, this will jump up significantly. It'll go from like 14% to 25%, right? Because right now, let's say, I don't really have anybody running in this screenshots who is consuming the high fidelity odometry at 100 hertz. If I pull up the user interface on the laptop, mind you, not on the Pi, right? User interface on the laptop, of course, and then have these guys send all the information over Wi-Fi to the laptop, right, at 100 hertz, you start to feel it, right? Utilization will go up because, again, as there are more consumers of the information, the producer of the information, has more work to do, because it's publish subscribe logically, but it's not a broadcast based mechanism. And so Again, when you have two people consuming the information, well, you got to actually push it out twice. And so these numbers will go up as other things are going on. But this is just a reference point. Again, the rawest core and master whatnot isn't really showing up here. I mean, it's like below 1%. Okay.
I
That's
thought the ROS core was doing the publishing and
No,
publishers.
it's just a directory. It's who you talk to find out, hey, it's like, hey, I want to consume the odometry information that is known as the /odom topic. Hey, how do I get that? Where do I get that from? Right. So it maintains that directory. It tells you, yeah, you got to talk to this IP address over there. Or maybe it's all local host, right? Doesn't matter. It just is a directory. And then there'll be a network connection peer to peer.
Okay, so that explains. I'll have more than one routine talking and grabbing the data.
Yeah. So again,
subscribing.
But it really, it's again, I have two pieces here that publish very high fidelity data at 100 hertz. Again, the moment you have people consuming this data, it'll be very noticeable in CPU usage. But anything that's happening at a lower rate, even if the amount of data is higher, like the LiDAR is arguably moving larger volumes of data around, right? But only at 15 hertz, and then again after 15 hertz I get vibration. So let's say 15 hertz, I'm moving a fairly large amount of data around. But because the rate is so much lower, it just tends to not translate into as much CPU usage. It's the high update rates and pushing the data out at 100 hertz, would definitely translate into CPU usage.
Okay, that's good to know.
So
Cool. Real-time debugging. Look at that.
Thanks, Chris.
Okay. Well, I don't know about you guys, but it's seeming a little slow tonight. Unless we have any other ideas, might I propose that we reconvene for the evening and then rejoin on Saturday, 1 p.m.
1 p.m. Good deal.
1 p.m. for Jack's Journey. All right, guys.
Sounds
Have a
good.
great night.
Till later.
Good night.
See you next time. Build robots.